Hello everyone, welcome back to this week's algebraic graph theory seminar. This week we have Monu Kadyan. He is going to talk about 4 types of integrality on mixed Cayley graphs over abelian groups. You need to unmute yourself, Monu. We cannot hear you.
Okay. Thanks, Tina, and thanks to all other organizers of this seminar. And this talk is going to based on 4 types of integrality on a particular class of mixed graph, and that particular class is mixed Cayley graph over abelian group. And the work which I will present here, it is a joint work with Bikash Bhattacharjya. So as many of you are know about integral graph, a graph is said to be integral if all the eigenvalues of its 0-1 adjacency matrix are integers. So, and this notion was introduced by Harare and Semink in 1974. And at the same time, they also raise a question that which graph have integral spectra. So in this talk, instead of integral graph, I will call it as a integral undirected graph, because I want to specify the undirectedness, because in this talk, I will discuss integrality of mixed graph. So now we will also see the definition of mixed graph. So let's first see outline. So this talk have divided into 3 main parts. First, we will go through some basic definition and one known result. Then we will move on the characterization of all these 4 types of integrality. And finally, we will go for the overview of the proof of the characterization of HS-integrality. This HS-integrality is one of the integrality out of these 4 types of integrality. So let's start with the definition of mixed graph. A mixed graph is a simple graph that can have both directed and undirected edges. So for example, it is a mixed graph, and underlying graph of this mixed graph is a simple graph, and you can see that the edge 1, 2 is a undirected edge, and the edge 1, 5 is a directed edge, and direction of this edge is from 5 to 1. Means a mixed graph can have both directed and undirected edges. And formally, we can say that mixed graph G is a pair of V and E, where the set V is non-empty and E is subset of Cartesian product of V with itself, and E does not contain those pair whose both tuples are same. So we will call to the edge UV as a undirected edge if both pair UV and VU are member of E, and we will call to the edge UV as a directed edge, and the direction of this directed edge is from U to V if the UV is a member of E but VU is not a member of E, and the direction of this directed edge is from U to V because UV is a member of E. So it means we can say, and it means if all the edges of a mixed graph are undirected, then we will call to the mixed graph as a undirected graph, and if all the edges of this mixed graph are directed, then we will call to the mixed graph as a directed graph. And in this talk, I will use this omega k notation for a primitive nth root of primitive kth root of unity, which is equal to x e to the power 2 pi I by k. So I will follow this notation for k primitive kth root of unity, and which is equal to this. So in this talk, I will consider only 3 adjacency matrices. The first adjacency matrix is the 0-1 adjacency matrix, and the 0-1 adjacency matrix of a given mixed graph G is denoted by the capital letter A, and it is a square matrix of size n cross n, where n is the number of the vertices, and its rows and columns are indexed by the vertex of given mixed graph G, and its UVth entry is 1 if the pair UV is a member of E. It means if the edge UV is a undirected edge, then UV and VU both will be member of E. It means both UV and VU entry would be 1. But in case of directed edge, so if we assume that the edge UV is a directed edge, then the direction of the directed edge is from U to V, then the pair UV would be member of V, but VU would not be member of V. So at that time, the UVS entry would be 1 and VUS entry would be 0. So for example, if the mixed graph, this mixed graph G is given, then the edge 1, 2 is an undirected edge. So both 1, 2s and 2, 1s entry are 1. But in case of directed edge, suppose 1, 5 is a directed edge from 5 to 1. So it is a directed edge from 5 to 1. It means 5 1th entry is 1, but 1/5 entry is 0. So in general, the 0, 1 adjacency matrix need not be symmetric. So eigenvalue may or may not be real. The second adjacency matrix is the Hermitian adjacency matrix, and it is denoted by the capital letter H, and it is also a square matrix of size n cross n, where n is the number of the vertices of mixed graph G, and its rows and columns are also indexed by the elements of the vertex set, and its UVS entry is 1 if the edge UV is a undirected edge. It means both UV and VU are member of the set E. And its UVS entry is I if the UVS entry is a O. The edge UV is a directed edge from U to V. And if it is the direction of the directed edge is from V to U, then it is -I, and otherwise it is 0. So for this example, the edge 1, 2 is a undirected edge. So 1, 2s and 2, 1s entry are 1. And the edge 1, 5 is a directed edge from 5 to 1. So 5 1th entry is I, and so 5 1th entry is I, and 1/5 entry is -I. So by definition of this adjacency matrix, it is a Hermitian matrix. So and all the eigenvalues of this matrix will be real because it is a Hermitian matrix. So if you replace I with the 6th root of unity and -I with the power 5 of 6th root of unity, then the resulting matrix will be Hermitian adjacency matrix of the second kind. So we just need to replace I with 6th root of unity and -I with the power 5 of 6th root of unity. And the notation for this Hermitian adjacency matrix of the second kind is the capital letter K. So it is the notation. So this is the example. So here the edge 1, 5 is a directed edge from 5 to 1. So 5 1th entry is omega 6 and 1/5 entry is power 5 of omega 6. And this matrix is also a Hermitian matrix. So all the eigenvalues of this matrix will be real. So corresponding to a given mixed graph G, we can have three different adjacency matrices. Based on the eigenvalues of these three adjacency matrix, we will assign the different name to the eigenvalue of mixed graph. So when we say that eigenvalue of the given mixed graph G, so it means that it is eigenvalue of the capital A matrix. It means it is eigenvalue of the 0, 1 adjacency matrix. So, and when we say that H eigenvalue of the mixed graph G, so it means that it is a eigenvalue of the capital H matrix, means Hermitian adjacency matrix. This H represents the Hermitian word. And when we say that HS eigenvalue of the given mixed graph G, so it means that it is an eigenvalue of the capital K matrix, Hermitian adjacency matrix of the second kind. So this H represents the Hermitian word and S represents to the second Hermitian adjacency matrix of the second kind. So it is eigenvalue of the Hermitian adjacency matrix of the second kind. So based on the integrality of these three eigenvalues, now I will present the definition of all four types of integrality. So when we say that G is H integral, so it means that all the H eigenvalue of the given mixed graph G are integers. So and when we say that G is HS integral, so it means that all the HS eigenvalues of the given mixed graph G are integers. And when we say that G is Gaussian integral, so it means that all the eigenvalues of G are Gaussian integers. And similarly, when we say that G is Eisenstein integral, so it means that all the eigenvalues of G are Eisenstein integers. So, and if the given mixture of G is a undirected graph, then we know that all those three adjacency matrix would be equal to 0, 1 adjacency matrix. So in that case, all those, in case of undirected graph, this term H eigenvalue, HS eigenvalue, and eigenvalue, all those three terms would be equivalent. So this will implies that in case of undirected graph, all those four integrality would be equivalent to integral undirected graph. So one can see these integrality as the extension of the integral undirected graphs. Now we will see some example, and we will also see the integrality of these examples. So these are the 6 mixed graph. The first mixed graph is a path of length 1, and it has one directed edge, and the second mixed graph is a cycle of length 3, and all edges are directed, and the third mixed graph is a cycle of length 4, and here these two edges are directed and these two edges are undirected, and this is the fourth mixed graph, and it is also a cycle of length 4, and all edges are directed, and this is the fifth mixed graph. Here only 2 edges are directed. So in that case, all edges are directed. Now we will see integrality of all those 6 mixed graphs. So here we can see that for the first mixed graph, the first mixed graph is H integral. Also, it is H integral, HS integral, and it is also Gaussian integral, and it is Eisenstein integral also. So means the first mixed graph satisfy all those 4 integrality. But in case of second mixed graph, it is only Gaussian integral, and it is only Gaussian integral and Eisenstein integral, but it is not H integral and not HS integral. So in case of third mixed graph, it is H integral, HS integral both, but it is not Gaussian integral and Eisenstein integral. And in case of fourth mixed graph, it is H integral and Gaussian integral, but it is not HS integral and Eisenstein integral. So by looking at all the integrality of all those 4 mixed graph, we can conclude that in general these any two integrality are not equal. But in this talk we will see a special class of mixed graph. In that class, both H integral and Gaussian integral would be equivalent, and HS integral and Eisenstein integral would be equivalent, and that class is mixed Cayley graph over abelian group. So now we will see definition of mixed Cayley graph. So let gamma be a finite abelian group and S be a subset of gamma that does not contain the identity element. So in this talk, I will consider gamma is equal to direct product of cyclic group Zn1 up to Znk, and of order n, and where n is equal to n1 times up to nk. So this set S, which is subset of gamma that does not contain identity element. So we will call to the set S as a symmetric set if the set S is closed under inverse, and we will call to the set S as a skew symmetric set if the set S does not contain inverse of its own element. So now we define a notation S bar. S bar is a subset of S, and S bar is a subset of S, and the set S bar contains all those elements of S whose inverse does not belong to the set S. Here I am using minus u as the inverse of u, because I am considering gamma is equal to this group under addition. So this minus u is notation for the u inverse of u. So it means if we remove all those elements of the set S bar from the set S, then this new set S, set minus S bar, would be symmetric set, and the set S bar is skew symmetric set. And we can see that any set S these two set are the disjoint partition of the set S, and we will call to this set as a this set as a symmetric portion of the set S, and we will call to this set as a skew symmetric portion of the set S. Now we will see definition of mixed Cayley graph, and this is the notation for the mixed Cayley graph, and the vertex set of this mixed Cayley graph is gamma, and the edge set contain all those pair AB for which B minus A belongs to the set S, and we will call to the set S as connection set. So if we replace this connection set with this new connection set S set minus S bar, then this mixed Cayley graph will be undirected graph, because the connection set is closed under inverse. So if the connection set is closed under inverse, then AB and BA both would be member of the edge set of this mixed Cayley graph. Similarly, if we replace the connection set S with the S bar, then this mixed Cayley graph would be directed graph, because all the edges of this mixed Cayley graph are directed. And we can see that if we find the edge set of this mixed Cayley graph, then it would be equal to edge set of this mixed Cayley graph union edge set of this mixed Cayley graph. Means this mixed Cayley graph is the undirected portion of this mixed Cayley graph, and this graph is the directed portion of this mixed Cayley graph. And similar kind of thing we can also see in the expression of eigenvalue also. So now we will see three different equivalence relation. The first equivalence relation on the elements of gamma, and if x and y are elements of gamma, then x is related to y if and only if y is equal to x to the power k for some k such that k is co-prime to order of x. The second equivalence relation is on gamma 4. Gamma 4 is a set of all those elements. Gamma 4 is a set which is subset of gamma, and it contains those elements of gamma whose order is multiple of 4. Means whose order is congruent to 0 mod 4. So if x and y are two elements of gamma 4, then x is related to y if and only if y is equal to x to the power k for some k where k is co-prime to order of x and k is also congruent to 1 mod 4. The third equivalence relation on gamma 3. Gamma 3 is also subset of gamma, and it contains those elements of gamma whose order is multiple of 4. Oh, sorry, multiple of 3. So if x and y are two elements of gamma 3, then x is related to y if and only if y is equal to x to the power k for some k, where k is co-prime to order of x and k is congruent to 1 mod 3. So these are the three equivalence relations. The first equivalence relation is on gamma, the second equivalence relation is on gamma 4, and the third equivalence relation on gamma 3. Now I will define the notation for three different collection of the subset of gamma. The first is B of gamma. So it contains those subsets of gamma that can be expressed as the union of some equivalence class under the first equivalence relation. The notation for the second collection is this D of gamma, and it contains those subsets of gamma 4 that can be expressed as a union of some equivalence class under the second equivalence relation. For the third collection, then this is the notation for the third collection, and it contains those subset of gamma 3 that can be expressed as a union of some equivalence class under the third equivalence relation. So these are the three collection which contains subsets of gamma, and it contains those subset which can be expressed as the equivalence class into some equivalence relation. So by using these four collection, now we will see the characterization. So it is the known characterization of undirected Cayley graph. This is this Cayley graph is undirected because here we have assumed that the set S is a symmetric subset of gamma. Means the set S is closed under inverse. So if the connection set is closed under inverse, then this mixed Cayley graph would be undirected. So we can call it as a undirected Cayley graph. So this undirected Cayley graph is integral if and only if the connection set is an element of B of gamma. Means the set S can be expressed as a union of some equivalence class under the first equivalence relation. And this characterization was given by Bridge and Mina in 1982. And in 2012 also, it was proved by using some different method by these guys. So this is the known result, which is the characterization of integral undirected graph. So here we have one condition that the set S is a symmetric subset. So in our characterization, we will remove this condition. So now here gamma be a finite abelian group and S be a subset of gamma. S be any subset of gamma. Then this characterization says that the mixed Cayley graph is H integral if and only if the mixed Cayley graph is Gaussian integral. And it is equivalent to say that the symmetric portion of the connection set S is an element of B of gamma, and skew symmetric portion of the connection set S is an element of D of gamma. So in case of mixed Cayley graph, this characterization is saying that both H-integrality and Gaussian integrality are equivalent. But in those 6 examples, we have seen that in general these integrality are not equivalent. And the same result I have also extended to any finite group when we consider the connection set is union of conjugacy classes. But for this talk, I am restricting gamma to the abelian group because we will also see the proof for that case. So this is the first characterization. The second characterization. So the second characterization saying that the mixed Cayley graph is HS integral if and only if it is Eisenstein integral, and it is equivalent to say that the symmetric portion of the connection set is an element of B of gamma, and skew symmetric portion of the connection set is an element of U of gamma. So in those 6 examples, we also show that this HS-integrality and Eisenstein integrality was not equivalent, but in this class it is equivalent. So now we will see the proof for this characterization. So now we will see the proof for this. So we will see overview of the proof only for this characterization. So we will prove that the mixed Cayley graph is HS integral if and only if the symmetric portion of the connection set is an element of B of gamma and skew symmetric portion is an element of U of gamma. Means we have to find condition on the connection set S for which all the HS eigenvalues are integers. So first we will calculate the HS eigenvalue of this mixed Cayley graph. So for that, first we define a function psi alpha. Let alpha is an element of gamma. So we have already assumed that gamma is equal to direct product of cyclic group Zn1 up to Znk. It means alpha will be equal to some alpha 1 up to alpha k, and alpha 1 is an element of Zn1 and alpha k is an element of Znk. So corresponding to this alpha, now we define a function psi alpha which is from gamma to C star, and psi alpha of x is equal to product goes from 1 to k, and here omega nj to the power alpha j xj. By using this psi alpha, now we define a vector x alpha, which is a column vector, and its rows are indexed by elements of gamma, and its xth coordinate is psi alpha of x. So xth coordinate is psi alpha of x. So if we multiply the column vector with the with the capital K matrix, then we can calculate HS eigenvalue of the mixed Cayley graph. So this will be the expression for the HS eigenvalue of this mixed Cayley graph. So here this gamma alpha is a HS eigenvalue of mixed Cayley graph, and it is true for each alpha belongs to gamma, where the first summation goes over the symmetric portion and the second summation goes over the skew symmetric portion. Now I will split this summation into two parts. So I will give the name for the first part as a lambda alpha and the second part as the mu alpha. So, and one thing we can note that lambda alpha is HS eigenvalue of this undirected graph when we take the connection set this set. Similarly, mu alpha is HS eigenvalue of this directed graph when we consider the connection set as far as this. Means that gamma alpha can be written as a lambda alpha plus mu alpha, where gamma alpha is eigenvalue of this mixed Cayley graph and lambda alpha is an eigenvalue of this undirected graph and mu alpha is an eigenvalue of this directed graph. So now we will see idea of the proof. The idea of the proof is that first we will prove that the mixed Cayley graph is HS integral if and only if their undirected portion of this mixed Cayley graph is HS integral and directed portion of the directed portion is HS integral. And for this undirected Cayley graph, we already know the result. So here this connection set is closed under inverse. So it is already known that this undirected Cayley graph is HS integral if and only if the connection set is an element of V of gamma. So it means we have to enough to show these two characterizations, this one and this one. Now first we will see an overview of the proof of this characterization. When the connection set is skew symmetric set. So first we define some notation. Let X be an element of gamma 3 and let R is belongs to this set 0. Let R is equal to 0, 1 or 2. Then define MR of X is set of all those power of X, set of X to those power of X which is less than equal to order of X, and that K is congruent to R mod 3. Means for when the R is 1, then it is K congruent to 1 mod 3, and when R is 2, then it is K congruent to 2 mod 3. So this is the first property of this M1 and M2. So if we take the inverse of each element of M1, then it would be equal to M2 of X. And if we take the inverse of this set, then it would be equal to M1 of X. And one thing we can see that this M1 of X and M2 of X both are skew symmetric subset of gamma. So if A is an element of M0 of X, then if we add A to each element of M1 of X, then this set would be again equal to M1 of X. Similarly, if we add A to each element of this set, then it would be equal to again M2 of X. So we will use of these two property in next some slide. Now we want to show that for X belongs to gamma 3. Now we want to show that this directed Cayley graph, because the connection set is skew symmetric set. So I am calling it as a directed Cayley graph or directed graph. So now we want to show that this directed graph is HS integral. It means we have to show that their HS eigenvalue are integers. So this is the expression for the HS eigenvalue of this directed graph. So it means we have to show that this expression is integer. So for each X belongs to gamma 3, for each alpha, we have to show that this expression is integer. So first we will fix that x and alpha. So let x belongs to gamma 3 and alpha belongs to gamma. Then we have two possible cases. Either this psi alpha is constant on each elements of M0 of x, or there is a in M0 of x such that psi alpha of a is not equal to 1. So if we assume the first case, assume that this psi alpha of a is equal to 1 for each a, means psi alpha of a is constant on M0 of x. So for each s belongs to M1 of x, this psi alpha of s will be equal to psi alpha of x, and for each s belongs to M2 of x, this psi alpha of s will be equal to psi alpha of x square. So for this case one, now we will for this case one, now we will prove that this expression is integer. So now we split this summation into two parts. The second summation goes over the inverse of M1. So inverse of M1 is nothing but a M2. So the first summation goes over M1 of x, the second summation goes over M2 of x. And for each s belongs to M1 of x, this psi alpha of s is equal to psi alpha of x. And for each s belongs to M2 of x, this psi alpha of s is equal to psi alpha of x square. And we know that the size of M1 of x and M2 of x are same, so we can take it common, M1 of x, then this mu alpha will be equal to this minus 1 size of M1 of x times this. And by our assumption, this psi alpha of x will be either omega 3 or omega 3 square, because when we are taking the power x to the power some 3, then this expression is 1. So it means this if it is a complex, if we take the power 3 of this, then by property of the homomorphism, it would be equal to 1. So it means psi alpha of x is equal to either omega 3 or omega 3 square. So in both cases, this mu alpha will be some integer. It means for the first case, this mu alpha is an integer. So in the second case, there is a belongs to M0 of x such that this psi alpha of a is not equal to 1. So we already know that mu alpha is equal to this expression where the first summation goes over M1 of x. Now we will split this summation into two parts, and this summation goes over the inverse of M1. So we replace M1 with M2 of x. So we remove this minus s with s, and we have already seen that M1 of x is equal to a plus M1 of x, where a is an element of M0 of x. Similarly, M2 of x is equal to a plus M2 of x. So this summation goes over that set when we add a with the element of this. Means we can take psi, by using the homomorphism property of psi alpha, we can take psi alpha of a common from this summation. Similarly, from here also we can take common psi alpha of a, and again this expression is nothing but a mu alpha. Means mu alpha is equal to psi alpha of a times mu alpha. So this will imply that 1 minus psi alpha of a times mu alpha is 0, and we have assumed that for that a, this psi alpha is not equal to 1, means this term cannot be 0. It means this will imply that mu alpha is 0. So mu alpha is 0 means it is an integer. So for the second case also, this mu alpha is an integer. So it means now we have proved that this directed Cayley graph is HS integral. No, so we follow this notation for the equivalence class of x with respect to the third equivalence relation. And if x is an element of gamma 3 and order of x is 3g, then the set M1 of x can be written as a such disjoint union, where the first union goes over all those divisors of g which are congruent to 1 mod 3, and the second union goes over those divisors of g which are congruent to 2 mod 3. So, and this is the equivalence of this is the equivalence class of x to the power h, and it is equivalence class of minus x to the power h. And this is the notation for the equivalence class with respect to the third equivalence relation, which is on gamma 3. So we will use, so now we want to prove that for each x belongs to gamma 3, that this directed Cayley graph is HS integral. Means we have to show that the expression of the HS eigenvalue over this connection set is integer. So this is the expression for the HS eigenvalue of this directed Cayley graph, and this summation goes over this connection set. We have to show that it is integer. So here we apply induction on order of x. So if order of x is equal to 3, then this m1 of x will be equal to equivalence class of x. So we have already proved that directed Cayley graph will be HS integral. So now we assume that the statement is true when the order of x is less than equal to 3g minus 1. And we already know that x is an element of gamma 3, so order of x will be multiple of 3. It would be either 3, 6, and so 3g minus 1. So assume that for all those orders, this mixed Cayley graph is HS, this directed Cayley graph is HS integral. So now we have to prove it for order of when the order of x is equal to 3g. So now we will use this disjoint union, which here we have add one condition that h is greater than 1. Means when h is equal to 1, then this equivalence class will be this. So we take it outside of this. So when the expression of the HS eigenvalue of this directed Cayley graph, when the expression of HS eigenvalue goes over this set, then that expression can be split into this disjoint union. So by induction hypothesis, when the expression over such equivalence class, by induction hypothesis, that expression will be integer. So, and the same expression over this equivalence class, that will also be integer by induction hypothesis. And we have already proved that the expression over this connection set is integer. So this will imply that the directed Cayley graph is HS integral. Means if we take connection set as a equivalence class, then this directed Cayley graph will be HS integral. So if we take any set S here, which can be expressed as a union of such equivalence classes, it means for that connection set also this should be HS integral. So now we have the following result. We say that if S can be expressed as a union of equivalence class under the third equivalence relation, then this directed Cayley graph will be HS integral. So now we will see proof for the converge part. For that, we define a matrix E of size n cross n, and whose rows and columns are indexed by the element of gamma, and its xyth entry is psi x of y. So we will take the use of the following lemma, which says that let gamma be a abelian group of order n, and V is a column vector of size n cross 1, and each coordinate is from this field Q of omega 3. And here one more assumption we have, EV is a element of EV again is a column vector, and each coordinate is a rational. And if we assume that the coordinates of V are indexed by elements of gamma, then the lemma says that the conjugate of x coordinate is equal to minus x coordinate. Similarly, for each xy belongs to gamma 3 and x is related to y under the third relation, then Vx is equal to Vy. And if the order of x is not multiple of 3, then the then the real part of Vx and V minus x are same, and imaginary part of Vx and V minus x are 0. So by using the by use of the following lemma, we can prove the convergence of our for the directed Cayley graph. So let S be a skew symmetric set, and this directed Cayley graph is HS integral. First, we assume that it is the set S is skew symmetric. So then it means it is skew symmetric means it is a directed graph. So we assume that the directed graph is HS integral. So now we define a vector V, which is from. Now we define a vector V of size n cross 1, and each coordinate is from this field, and whose coordinates are indexed by elements of gamma, and its x-hat coordinate is equal to omega 6 if x is a member of the connection set S, and its x-hat coordinate is power 5 of omega 6 if x is from S inverse, and otherwise it is 0. So if we multiply the vector V with E, then its alpha coordinate would be HS eigenvalue of this directed Cayley graph. And we have already assumed that this directed Cayley graph is HS integral, means this alpha coordinate is integer, and it is true for each alpha, means thus that this vector EV is a member of Qn. So by the previous lemma, we can prove that by the previous lemma it will satisfy all three conditions of the previous lemma. So this will imply that the connection set S is a member of E. So now we have proved the following characterization, which saying that the directed Cayley graph is HS integral if and only if the connection set is an element of E of gamma. So now we will see the proof of the other part when so this is the characterization for the directed Cayley graph when it is HS integral if and only if the connection set is an element of E of gamma. So now we assume that S be any subset of gamma and it is a mixed Cayley graph. If S is any subset of gamma, then this would be mixed Cayley graph. And we assume that this mixed Cayley graph is HS integral, and this is the expression for the HS eigenvalue of this mixed Cayley graph. So if we subtract gamma minus alpha from gamma alpha, then it would be equal to this summation where the summation goes over the S bar. So again, we define a vector V in such a way that it satisfies the previous lemma. So from that previous lemma, the previous lemma will imply that the S bar is an element of Q of gamma. If S bar is an element of Q of gamma, then S bar union S bar inverse will be element of B of gamma. So if it is a B of gamma, then by known result, this summation is integer because it is eigenvalue of the undirected Cayley graph when we consider this as a connection set. So and mu, we can write mu alpha is equal to this, where the first summation goes over this, which is equal to this expression, and 1/2 times summation. The second summation goes over S bar. So we have already see that it is integer and it is also integer. It means this mu alpha is a rational. Means mu alpha is a rational algebraic integer. So it is a rational algebraic integer means it is an integer. So this will imply that this directed Cayley graph when we consider this connection set is HS integral. If mu alpha is integer, so this will imply that it is this directed Cayley graph is HS integral. So now this is the directed portion of this mixed Cayley graph. It is directed portion. And we have already, so we by assumption gamma alpha is integer, and we have already saw that mu alpha is integer. So this will, and we know that lambda alpha is equal to gamma alpha minus mu alpha, and both are integer. So this will imply that lambda alpha is also integer. So if lambda alpha is integer, means this undirected portion of this mixed Cayley graph will be integral. Means this it is HS integral. So here the connection set is closed and inverse, and this mixed Cayley graph is undirected. So instead of HS integral, I am using the term only integral because it is a undirected graph. And in case of undirected graph, all those integrality are equivalent. So that's why I am using here integral word. Means we have so that the mixed Cayley graph is HS integral if and not. This will imply that their undirected portion and directed portion are HS integral. And converge also we can easily prove by just looking at the expression of the eigenvalue. And this undirected Cayley graph is HS integral if and only if the connection set of this undirected graph is element of V of gamma. It follows from the known result, and we have already seen the proof for this portion that this directed Cayley graph is HS integral if and only if the set S bar is an element of E of gamma. So now this was the overview of the proof of the HS integrality. Thank you.
Thank you for the talk.
If anyone has some question, then can ask me.
Yes. So any questions for Monu?
I guess I have a question. It's kind of tangential because, I mean, there's something very special about Gaussian integers and Eisenstein integers, and that relates to looking at exponents modulo 3 and modulo 4, right? But does any of this analysis work for if you look at difference congruence classes, like y is congruent to x to the k if k is congruent to 1 modulo something else besides 3 or 4?
Okay. So you want that instead of this k congruent to 1 mod 4?
Yeah, so do these equivalence classes make sense for moduli other than 3 and 4?
So here x and y are from gamma 4, means order of x is multiple of 4.
Yes, I understand. But suppose instead of looking at gamma 3 and gamma 4, I look at gamma g for some other value of g. Can you say anything about the eigenvalues of those Cayley graphs? They won't be integers, but they might be nice in some other way.
Okay. So if x and y are from gamma g, then can we define some equivalence class like this?
Yeah, I'm just curious because I've never thought about these equivalence classes before, and they seem quite interesting.
Okay.
Yeah.
So equivalence class of this relation are skew symmetric set, and these equivalence class does not contain inverse of its own element. Because here k is congruent to 1 mod 4.
Yeah, I mean, there's clearly some nice number theory going on in the background here, but I'm just curious about that. Oh, that's all I have. I mean, I have no specific question really. I'm just kind of interested in the whole setup. It's very nice.
Means if k is co-prime to order of x, then k would be either congruent to 1 mod 4 or 3 mod 4. So these are the only two possibilities.
Right.
So if we see the equivalence class of x, then it would contain those power of x which co-prime of this, and if we see the equivalence class of minus x, then in that case, this k will be congruent to 3 mod 4. But you are saying that if we, instead of 4, if we take any integer like g.
Yeah, so
Then,
what about if you looked at this with x equals, sorry, y equals x to the k, or for some k that's
so
full
instead
prime
of
to
4,
the order of x, but where you've got, sorry, elements of order 10 or something like that. I mean, there's going to be, you're not going to get integrality constraints, but you might have some other subfield of the complex numbers that contains all of the eigenvalues. Some other subring. Yeah, I don't know. It's just a speculation. I'm curious about it. I think it's a very nice subject. So thank you very much.
okay.
It's a very nice result too, by the way.
And I have extended all the result to any finite group gamma also. So in that case, we have to assume that the set S is union of conjugacy classes.
Oh, for non-abelian groups.
Yeah, for non-abelian group also, and we have to add one condition that S is union of conjugacy classes. Then all this result will be remain same,
Very
remain
nice.
true.
Very nice. Okay, thank you.
Yeah, thank you.
Sorry, did you say even if like this gamma is not abelian, this result still holds?
Yeah, for non-abelian group also, we have to add one more condition that S is union of conjugacy classes.
Oh, okay.
Then this result will be remains true.
Okay.
But if we go for the proof of for that in that case, then we have to use representation theory.
Okay.
So in case of abelian group, we are just playing with the expression of eigenvalue and some basic property of abelian group. But in general, it is not so simple like this.
Oh, I actually also have a question. So you said S has to be union of conjugacy classes. How does that help your result that S is a union of conjugacy classes?
So S is union. So if we see the expression of the eigenvalue of undirected Cayley graph. So can I share a different screen?
Yes, please.
Can you see this?
Yeah.
This PDF?
Yes. Yes.
Okay, I have to. When the connection set is union of conjugacy classes, then if we see the expression of the eigenvalue, so this expression will be algebraic integer when the connection set is union of conjugacy classes. Otherwise it would not be algebraic integer. And if that expression is algebraic integer, so I am not able to make it zoom.
Okay.
So if you just look at this, so when S is union of conjugacy classes, so then this expression will be algebraic integer, and it is important for us because when we prove that it is rational, then because it is algebraic integer, then we can directly say that it would be integer.
Okay, I see. Thank you.